Good morning, everyone. My name is Graham Blois. I'm a core developer for Wireshark and the moderator for this session, which is session 03 of SharkFest EU Virtual 21. And the session is about chasing application performance with Wireshark. And your presenter is Matthias Kaiser from Germany. This session is being recorded and will be available on the YouTube channel and the retrospective website subsequent to the conference. And Matthias today will run through a section of introductory material about the problems he's looking at, and then 2 case studies, and then there'll be a Q&A at the end. He's already provided a zip file containing the captures and profiles used today. I'll just post it in the chat, and it's also in Discord. I shall now hand over to Matthias.
Hello. Thanks, Ram. Welcome, everybody, to my session, Chasing Application Performance with Wireshark. I hope you can see my video and in a good condition and everything is well received on your end. I hope you can follow my audio with a proper quality. I'm Matthias Kaiser. I work at Expertise, German-based training consultancy company. I live in Hamburg. I'm married. I've got a little daughter of 13 years old. Well, I'm here because, well, I love packet analysis. I've been in the area around for quite a while, and I work as an instructor and as a consultant. Looking at packet has become a habit for me for the last, let's say, 20 years. I started my troubleshooting career at Sniffer University. I was a staff instructor at Network General. Well, that company got acquired by Network Associates. I then, after they laid me off, I worked as a freelancer and wrote my own course material on Ethereal, and Wireshark. For the last 12 years, I've worked for Expertise. Well, and my motto is every trace file hides a story. Well, you gotta uncover it, the story, and try to tell it. And this is what I will try to do when you will follow me through the 2 case studies. So, I've got 4, or let's say 3 case studies available for you. I will cover just 2 of them, just for the lack of time. For when I go through all the material, the stuff on the theoretical side, which is which is an absolute must, plus 2 case studies will make up roughly an hour, and that will leave us some time for the feedback session, the Q&As after, let's say, at 12:45 my time. Of course, all trace files have been anonymized and sanitized with Trace Wrangler, thanks to Jasper Bongartz. Now, my agenda for you for today is, so I'm going to use the laser pointer of PowerPoint. Well, why I picked this topic? Well, chasing application performance using database applications. Then a little bit of before we start working with the case studies for this presentation, and as it's meant generally before we start troubleshooting and looking at trace files. I'll have a sample database flow, which used to become a typical one for me and for my cases and problems I ran into at the customer side. And from the 3 case studies I prepared, I'm going to present to you number 1 and number 3. For every case study, there is also a Wireshark profile within my zip file. So if you like, you can follow it on my screen. I will show you the do's and don'ts, well, the trials and errors and the success getting through those case studies and solving those problems. You could also work on it, well, when you're back at your office or back home. At the end of the day, we're going to look at the application metrics for Wireshark for looking at database applications. So this is just a little bit of a wrap up. But let's start. Why I picked database applications? Well, I'm a network engineer. I love looking at networks, and using Wireshark and looking at trace files is really fun. It should be fun. It will stay fun, and it will never get boring. I promise you. Well, applications drive all the processes almost everywhere. That means for every process within a company or even at home, whatever you do, you go onto the internet, you need to have an app. And if that app is running and is performing well, then we're in business. Otherwise, we won't be happy at all. Well, in the corporations, the most critical applications could be, well, either voice or video, but it could also be the databases. Well, databases could either not work at all, or they are slow. And if an application is slow, most people I ran into, they look at Wireshark and they raise the one single question: why is your network so slow? So networks are always suspicious for being for bad performance. But in this case, well, most of my cases, it's not the network. It could be something else. And one of my mentors once said, well, if it's a network problem, I can find it using a packet analyzer. If it's not the network, I can at least show you where to start with the troubleshooting process. And even, network is fine, but since we are running into a phase of software-defined networking where controllers, well, silicon controllers will tell servers and the network devices what to do. So we better understand how applications work and how we can analyze them in Wireshark. But before we start looking at packets, well, number one, have a plan. Don't just open a trace file. Don't just capture some traffic. Define your goal. What are you trying to achieve with Wireshark? Well, just to waste some time, it could be a goal. But if you've got a goal on a corporate basis, well, you rather put it on paper, either for yourself or for your customers. Describe what the problem really is, find out who's affected, whether it is just by means of a single PC, a single user, well, maybe a bunch of users within a subnet, maybe one location, all locations. Just define what the problem is about and who is affected, and check the severity. And then identify what applications and what the application flow is about. And the most critical thing for me is find out when the problem occurs. Is it a permanent thing? Because then it will be a replicable, repeatable process, or sometimes, and they are even harder to troubleshoot if things are sporadic or in what we call intermittent problems. So you never know when the problem is going to happen, but you know that it's going to happen. And well, the one truth I ran into quite often is whenever the analyst with Wireshark is looking at the problem goes away, maybe out for lunch. And you can be sure when you leave the campus, the problem will turn around the corner and say, hi, I'm here again. Well, since this Wireshark geek is off the ground. It's always that way. Long-term capture would be good. And please, if you defined your goal and describe your problem, you don't need to guess around. Please stop guessing. Look at the evidence, at the packets, what is there. Only what we see, and when the data is clean enough, then we can start with a troubleshooting process. Now, next thing is when you are in charge of doing the capture yourself, know the application and know the traffic flows. Well, where is the client? Where is the server? Do we have a multi-tier environment with multiple servers in a row? Well, and where does the application actually run? And really that defines your capture location. Where do I see the interested traffic? Well, I'll get back to that within a second. And then if it's a permanent problem, just pick a typical action and pick one user which kind of reported that problem maybe most often. Get this gentleman or this lady involved. They feel a lot better, and that you can kind of give them the opportunity for contributing to the problem, or let's contributing to the solution. Most of the time, if you involve users being quite that are quite angry, they will still try to help you. If it's an intermittent problem, you got to do some long-term analysis, maybe with T-Shark running in the background, and well, use this option to write into multiple files. So that's the capture piece. And then for the analysis, well, prepare your Wireshark and especially work with profiles. For every single case study, I've got a profile. For every single case at the customer side, I've got a profile. For every single protocol, and even for the CTF, I created the profile. Well, and don't mess around with it too often, and save them for sake. Now, then filter your trace file on those known IP addresses, maybe ports, IP addresses of clients, of servers, and then try to identify the user activity. If your one typical action is actually shown in Wireshark, then you can start the analysis actually. And please know your key metrics for your application, whether it is, well, throughput for bandwidth oriented applications. It could be, well, round trip time. It could be response time for a specific application. Well, mileage varies. People in the US were tempted to say it depends on the application. Find out what is critical. But in most cases, the key metric is time. How long does it take for one activity, for one transaction to complete? Well, if it does complete. If it doesn't complete, then we've got a problem. The thing that the application does not work at all. That's a different process. Well, for us, it's about performance. Now, my sample database flow here is a simplified one, and I'm well aware of that. I picked a client with a front-end connection doing maybe HTTP or trying to access an application server with an embedded web server applet as well. Now this application server will receive the requests from the client and then go over to the database server, issuing a series of SQL queries. Well, that SQL, that's the critical stuff. Usually, very often with a request and response, request and response, and request and response, and this goes on and on and on until the final response comes back, and then, well, the result is being computed on the app server, and the response is being sent over into maybe a browser window visible for the user. Well, I'm aware that this monolithic infrastructure has changed over time. It could be not only one app server, but maybe 20 or 50 of them. If it's just one, then we can do the analysis like this. Well, out of all, let's say out of all my database cases I did with on customer premises, well, there was in 80% of all times, we still had those one app server, one database server, and space to capture. Now, The front end is something like one request, one response. The back end here is usually many request response pairs. We call that an application turn. Well, once back and forth, that's an application turn. And there could be a potentially high number of application turns. So the backend is quite sensitive to number one, round trip time, the number of turns, and then, well, the response times for those request response pairs should be okay. Well, you name it, what is okay or not. Now, and what we heavily will depend upon is the client server architecture. Well, when you do when you determine your capture locations, your capture points, you got to know where the application is actually running. You could end up with a fat client. The fat client on the app going to the app server into the database. But in many cases, you'll find terminal server services and then virtual desktop infrastructure. VDI clients, well, where the thin clients would only remote control. In VDI, I need an entire session, let's say, well, an entire operating system, and on the terminal server basis, usually just a user session or a single shared application. Well, it really depends where you on this architecture where to put your capture points. Well, those will fly in as the red dots here. Well, with terminal servers, your application from the user perspective will be on the terminal server or the VDI client. You could also, for fat clients, capture on the fat client. Well, you could also do this when you go to a cloud provider. Well, better is if you get a chance to capture at the application server, no matter whether it is in a cloud environment or at your local data center. Well, that depends. Well, but the client-server architecture does have a huge impact on the performance of the overall application. Now, having said that, well, around 15 minutes into my presentation, I want to start with the first case study. So that should leave us plenty of time, and the theory comes last, like talking about those metrics, key metrics to evaluate. One thing before I start, one thing I want to emphasize. Let's go back again. Capture has already been done. Preparing the Wireshark with the profiles has already been done. Filtering the trace file has already been done. Bear in mind, this takes most of the time before you actually start with your trace file. Once your trace file is clean and is clearly showing the user data for that, let's say, specific activity or action of the user, then going through the key metrics and identify, well, potential problems will not waste too much time anymore, because you've got a repeatable process. So bear in mind, this has already been done, looking at our trace files now within this session. So seatbelts fastened, off we go. Now, the first problem was a customer called up and said, hey, we've got a process. It was actually a weighing process of pallets full of steel. It was quite heavy. And they had a remote control, like starting off the transaction. And the transaction took quite a long time. So we had high transaction times for this database transaction. And it was a permanent issue. Permanent means it was a repeatable, replicable process. So that was the weighing process we were looking at. Now, we did a couple of trace files. And if it's a repeatable process, you gotta have a reference in place. What is good? Because if things already are slow and you don't know what good means and how long this, let's say, this transaction could actually take, well, if it was in best shape, then it's a bit tricky because you can always improve. The question is how far. So, but the suspect again was the network. Well, they had those twisted pair cablings and they failed on the Cat6 test. And from that moment on, when this became public within the company, well, all problems related to this site were closely linked to the network. Well, is it the network? I don't know. We'll get to that later. Now, this is the map. And what I always do when I come to a customer, I don't want to see all those network maps around. I just draw my own. Where is the client? Where is the app server? Where is the database server? Well, and we had site 1 with a problem, and we had a reference site with no problems being reported. So we could have we actually have a reference to point to. Now, front end and back end flows visible, while my capture locations are at the app server, because you'll see the incoming flow and the outgoing flow. And while the database server was located across a 4 megabit link leased line at the provider's site. So, well, let's move to the trace file. So I've got my Wireshark hooked up, and in case number 1, I take this is the site 1 before. This is before the change when the problem arose. What I already did, I added the names to the IP addresses. If you look down at the internet layer, where those source and destination addresses are located, well, I already assigned those names. Now I can switch it off and on, but they have been saved through this option. Right click, edit resolved name. So these are already in the trace file. They gotta be saved after you add the names into it. But this is a perfect way how to show, well, a third party what this IP address is about. Where's the client? Where's the application? And I already assigned, you see that, the colors. I also added some of the filters, like a front end for site 1, back end, and so forth. And this was a repeatable process. Now let's have a look at how long it took for one single session. Front end, site 1. This is just one IP address, and the second one, you'll see a client goes to the app server, and there are some major delta times. At the end of the day, the front end process took 40 seconds. Well, it was a weighing process where some staff waiting for a receipt of the weighing process. And 40 seconds is a nightmare for someone that has got tons of work to do. And believe it or not, it was tons of work, since we were weighing steel pellets or pellets full of steel. Well, 40 minutes was bad. Now the question is, what did the reference site actually say? Well, the reference site, which is 1 minus site 2 reference, I also prepared this window already. It would also have client to application server. Well, client and application server were on the specific sites where the database server was just one specific one. Now we had that front end session. If we filter on front end site 2, the reference, well, this column for the relative time shows the time from frame number 1. Well, it can be moved around if you add, right-click a time reference. We'll get to that later. Well, the reference was 15 seconds, which was a lot better than 40 seconds, but still waiting for 15 seconds for one transaction to complete was quite painful. So we rather we wanted to check if those 15 seconds could already be improved somehow. Now the question is, who's to blame? I don't want to put the blame on somebody who doesn't deserve it, and it's by means of, we should not blame people for any bad performance. We should just pinpoint the problem. Is it the network? If it's the network, then fix that first. Now here we've got the front end session, 40 seconds. If we look at the backend session, and here the backend session is a series of, well, SQL calls. And since the backend session starts with packet number 3, I could take a right click, set the time reference just to calculate the relative time from the back, and go further down. And we'll end up on the backend side is, well, roughly 38 seconds out of 40. Now, out of those 40 seconds, most of the time was spent on the backend. Well, 2.26 seconds is still a lot. Well, but start with the important piece with the massive delays here. So we rather take this route and look at the rest. Now, how can we identify who is responsible for those 37 seconds? Well, one thing to bear in mind, delta times. Delta times show, let's say, excessive delay between those packets, and you may see delta times that already exceed 1 second. 1 second delay is a lot. Here you see a packet with 3 seconds. Now, one thing is, I always take a filter TCP.length greater than 1. Why that? I wanna, hang on. I would like to just see application data. Well, anytime when a packet is sent, it has to be acknowledged. Well, and the acknowledgement has got either 0, and if it's a kind of a keep alive or probing issue by TCP, it could have a TCP payload length equals 1. So everything that where the TCP length is greater than 1, it should be application data. So that's something to bear in mind. Now, so all the acts have been eliminated. Looking at that, I could sort by delta time and look at the large delta times if there were any. Now, if you look at the delta times, just look at that here. Delta time, this column sorted by this, 7 seconds, 4 seconds, 3.5, 3 point something. Well, that's an awful lot, an awful lot. And now the key thing about this is when you saw the delta time, it is not being recalculated. Then you check on the source. Now here, 7 seconds are caused by an application, by the application server, because the predecessor, the preceding packet was almost 7 seconds away. And then after those almost 7 seconds, the app server will kick in and say, and send something to the database server. Hello, this is me. And the database server, yes, glad you're back. Okay, sorry. But so if you look at those huge delta times, everything that is beyond maybe half a second, maybe 1 second. So look at this, 1, 2, 3, 4, 5, 6. They were all caused by the application server. Plus, we've got two packets, right click and mark, 2 packets where we had 2.4, 2.1 equals 4.5 seconds delay caused by the database server. Now, both have to be taken into account. The 4.5 on this end, and well, this is roughly, well, again, down there, it's the application server still in. Well, I did the math myself. It's 32 seconds on the app server side and 4.5 seconds on the database server side. Well, and that is almost the 37 seconds of pure transaction time. So the findings here are, well, the application server is the key station to focus on. Now, the thing is, if you identify, well, a source to troubleshoot, the solution is not seen within Wireshark. The why is not seen. You got to get up from your trace file and actually go there and look at the station. Well, guess what? Guess what the server guys would actually say to you? Well, my server is just being bored. Well, how can you say that? Well, I pinged the station. Well, just one ping doesn't make a bad performance. You got to look at the application. So basically, this is what we were looking at. Plus some 1.43 seconds on the client side. Well, it was not the user waiting for 1.43. We told the user to do a click and then keep their hands off anything. Because if there is a delay on the client end side, I want to know whether it is the client PC or actually the user. But my finding just now is the application server needs to be checked. And so basically what I already did, or what I just did, is also in the presentation. I don't want to go there. It's just for the reference of yourself if you want to follow it up with a trace file and everything. So 40 seconds transaction time, 15 seconds on that end, and the huge delays spotted there. Okay, here we go. So the database server accounts for 4.5 seconds. The app server for 32.6 seconds. Give me a break, a large break. Well, I could brew some espresso and even drink it within those 32 seconds. Now, comparing site 1 to site 2 also showed that those huge delta times would not show at site 2, at my reference site. So there was a bit of a difference between the app server on site 2 and the app server of site 1. Now, coming to its first solution, the app server seems to take many long breaks. Plus, the app server showed, I haven't covered that, but it showed also high acknowledgement times. That is an indication that the entire machine and not only the application ran into overload. Also, we saw a couple of retransmissions. Well, next step, we checked the application server health and the application itself. And then maybe take care of the retransmissions at a later stage. Don't forget about them. Now, what we found on the app server was, well, the application was a data, well, they call it a database. It was Microsoft Access, huge in size and had not been, well, re-indexed, reorganized for months. The machine was a bit overloaded. It had 256 megabytes of RAM. Oops. Where for the very early Bill Gates, this would have been a fortune, but for us, not at all. So the machine was, it had enough RAM to look at to deal with the disks, but nothing else. Now, what we said was, let's reorganize the database on this app server. Well, some call it Access, some call it a database. That's different. And so we did that, and we got site 1 after. And then it was the plan to add some more RAM to the machine later. But let's look at the improvement, at the level of improvement afterwards. So my trace file for case number 1, site 1 after It just opens on my second screen. Let me pull that in. I hope it will show up. App analysis 1. Going back to the front end side, filtering. Well, that does make a difference. Please note the final packet, which used to be an 8.3 seconds. So that's almost half of your reference site. Okay, so basically this is an improvement. If I take that and look at just at the application data and sort again by delta time, oops, repeatable process within Wireshark, you'll save a lot of time going, fiddling around with your profiles. You'll see 2.8 by the database server, 1.2 by the database server is a total of 4 seconds. Yeah, the 1.34 seconds, that rings a bell on the client end side, and the app server was quite fine. Hey, problem solved. Do you think we're done? Well, for the most part, yes, but we didn't add the RAM yet. And please, whenever you got the first problem solved, there could be a second and even a third. We still had some retransmissions, and I pulled up the expert in this after trace. We still had some retransmissions, duplicate X, previous segment not captured. Well, why would we have retransmissions? Well, the solution was there was a link between a switch and the router. Let's take it British today. The router, not the router. They had a duplex mismatch, and so they would eventually drop packets, but they put them out of sequence. Out of order is not out of use, but it is out of sequence. So we had a packet reordering, which caused the retransmission. Well, after the duplex mismatch was fixed, then those that packet loss plus the retransmission went away. Yep. So, and that is the solution of this case study number 1. Lessons learned here: an overloaded app server can cause high delays. Filter out the X. Look at the large delta times. You could also check the flow graph. That could also help if you haven't got too many packets. Well, this time reorganizing the database helped. Adding RAM helped as well. And duplex mismatch can cause packet loss, drop packets, and retransmissions. Well, on a low utilization, you'll find packet reordering also ending up with retransmissions. Important for me, don't stop after you identify the first problem. There might be more. Okay? And that concludes my first case study. So, by the way, questions and answers on both case studies will be at the end. So you'll have the chance to raise any questions. Plus, I will be in the Discord, on the Discord server, on one of those voice channels for the Zoom One discussions. If you want to raise additional questions like how did you do this, how did you do that, what worked, what helped, what did not work at all, how long did it take? Well, you can meet me over, let's say, what we call the lunchtime break, if you want. So, ready for number 3? Breathe. Well, that was for myself. Case study number 3. Well, it was 4 years ago, actually. I had 3 weeks, or let's say 2 weeks time, before I before I planned on a paid time off and going on holidays. I had extra time scheduled for writing some courseware for my company. Well, it was actually 3 weeks, and I fell sick for 1 week. I came back, and before I could hook up my computer, I received a phone call. Hey, you've got a conference meeting. In 20 minutes. And I said, well, better not. It's I fell sick. Yeah, whatever. The case was we had an agency for temporary work located in Germany. After moving their data centers to a new service provider, the accounting software, which was their major application, had severe performance problems. Well, those agency for temporary work, at the end of a month, the accountants will have usually have 2 days of getting their paperwork done. And then in order to get all those invoices, well, calculated and also printed and sent off to the customers, the system had to work on the database. And usually the calculation of all this took 8 hours with the old service provider. Now, after they had a test run, they estimated that this calculation or computation would take at least 24 hours or even longer. Well, the problem is when you've got 12.5 million euros per month of revenue, and well, the penalty for delayed processing was 10% of the revenue. They were threatened with more than 1 million of penalties. And so they were really upset. And the service provider called us up to, it was me and a colleague of mine, let's check everything. They had no clue. Now, let's get started here. Also, was it a permanent or was it a temporary thing? Well, we were lucky it was a permanent issue. So we could take just one user activity and go from there. Now the network map was quite interesting. Customers were at different sites across Germany. They were taking, the data center was using the virtual desktops again. So the protocol on the front end was PC over IP. So that's a UDP-based application for remote controlling those virtual desktops. Now, when the virtual desktop accessed the database directly, that took quite long. Now, they had a temporary check whether this, well, long transaction time could actually be improved, where they put a terminal server right behind the VDI client. So the VDI client, well, the client remote control, that's the blue dotted line, the VDI client, and the VDI client actually remote control the terminal server, and the terminal server accessed the database. So the application was running on the terminal server. And the only piece of hardware being involved, actually, it was a software-based firewall involved here. Now that's the terminal server. And it turned out that the performance was quite better when the terminal server was introduced rather than the VDI client itself. But we didn't know why. Plus, we needed to identify where to start. Is it the WAN side? Is it the VDI client? Is it the firewall? Is it the server? Is it? And why is the terminal server so much faster? Good. Well, our capture locations, our capture points are, well, for the direct session, it was the VDI client. Again, we were using T-Shark running in the background with system rights, so it wouldn't actually interact with the user session. And T-Shark has got the minimum impact on the performance. Don't try to do that on the GUI, on the Wireshark GUI running in a VDI environment, especially when the VDI environment has got already poor performance, and that could be suspected. Now, this is the setup here. Well, I'll come to that later. I'll come back to that later. Now, we needed to have one single process just to identify the source of the problems. Like, where do we start looking at? Where do we start troubleshooting? So we picked something when the application was actually started, user login. Why that? Well, we already had a baseline in place. And according to that baseline, It was just the first attempt, but it worked out that well. So it was the last trace we did, looking at that user login. So we repeated that process, user login, like hitting enter and watching the screen fill. We repeated that multiple times. And we had a repeatable process since the number of packets and the flow was, let's say, was really similar. So we have to check whether it is a repeatable process. If yes, we can start with the analysis. If no, we got to find a new, well, user activity within our application. And so we took traces for VDI users and for the temporary terminal server users, just for the sake of comparison. Now, there is one trace file for VDI, one sample one, and one for the terminal server. And we'll do the analysis right now. Now, let's start with the results first. The VDI client for that one transaction took 31 seconds, roughly, number of packets. The terminal server, well, TS, 10 seconds. The baseline, it was just a guesstimate by the client, or by the it was 8 seconds, while number of packets unknown. Well, the question is, why is the VDI so slow? So who is wasting time? Why is the terminal server much faster, and where's the bottleneck? And by the way, is it the network? Yes or no? Funny story. I promise you. You will be surprised. Now, let's go off to the application itself. Closing this. Well, let's close all former trace files. I will start with the VDI client. Looking at the times. Okay, for 12:45 should be the end of the session plus the questions. And you know, if you don't have questions, I've got another trace file for you just to digest before lunch. So the VDI client has just, well, it's the client, it's the database going back and forth. It's a TDS protocol, tabular data stream, which is the, well, protocol used by, in this case, it was a Microsoft SQL database system. So sometimes with some of the databases, you'll end up with a specific protocol that is well known. I know this question was raised. When is additional support for database applications and for database protocols being added? And again, well, Gerald noted that there is no limit, but it's maybe by means of time. And well, I could add some extra things onto my wish list. So TDS was the application. Already, well, application analysis 1 is not good. Let's take analysis 3. And plus a control, an R for reload. So it would, after changing my profile, somehow the name resolution has to be rerun with a view, reload, control R, it shows up again. So it's the VDI client and the database server going back and forth. The question is, who is wasting my time? Well, the maximum time is from the very first to the very last. It's 32.1 seconds. It's quite a long time for a single screen to load. So, well, it's not the worst performance I've seen in the past years, but it is pretty bad. So no colors there. It's just the VDI client and the database server. Now, same story, same thing here. I filter on just the application data. Click. So all the X have been eliminated. Yep. And so you'll see in the status bar down here, it's displayed, it's 98.5% of all the packets available. So 1.5% for X. That's quite a good number. Now, again, to get an indication where to start, sort by delta time. Sorting by delta time, descanning. Oops, hell. Sorry about that. This is a delta time of 12.7 seconds. This is a delta time of 1.5 seconds. This is a delta time of right-click mark. This helps me identify those specific packets because I can go do an edit and just jump to previous mark, next mark. So this helps me jumping there before I start with the evaluation of the rest. Okay, here and there. So who's to blame for these major delays? Well, it's the VDI client. The VDI client is waiting for quite a long time before it actually kicks off another request to the database server. Is the database server to blame? Well, the maximum response time for the database server is 141 milliseconds. That's the absolute maximum, which is not too bad at all. And if I took that, like if I wanted to see just the database server, just for the sake of showing it to you, I'm gonna take the database server being the source address, do a left click, click and hold, pull up. This is a perfect way to extend my filter. And I do an end. I want to see all packets from there. Well, the delta times here haven't really changed a lot. So let's get back to my application data filter. So 12 seconds, 1 second, 31 seconds is the maximum. Well, the baseline showed 8, and the terminal server actually showed 10 seconds. Now, where to start? Again, it is the client. For the visual folks of you, if I go to statistics and the famous or infamous graph, I already prepared that as well. I hope it didn't break. It almost broke. But I better not eat something in the matrix. From server, from client, and if I take the interval of 100 milliseconds, now it will rebuild. If it doesn't, please hit the reset button. Do you see those large breaks? Here, that was the first piece, and then comes almost 2 seconds, and then the 12 seconds, and another one here, and another one there. So it's a graphical view on that kind of problem. Just one specific transaction. So where do all the breaks come from? I don't know. I have to check on the VDI client. Well, when I compare it to the terminal server, which loads again on my second screen, I pull it over here. So terminal server session is section number 3, application data. That's my filter on delta time, descanning. Well, the 12 seconds is not there. The maximum is 1.2 seconds from the terminal server. This is where the application is running and the database server would actually wait. Well, and on my hex screen, you'll see the payload has been removed by Trace Wrangler. Well, that's the right thing to do before starting a presentation like this. Now, so that this terminal server was a lot better, and that also is visible in the IO graph, but it's just a different way to looking at those things. So, terminal server, going back into my presentation. That's what I actually did. VDI client, the graphical view on the I/O graph. Well, the comparison to the terminal server, it's just one trace file. I usually take the minimum of 5 trace files, and if I see the same pattern within all 5, I take an estimate of, okay, this should be normal operation. If time varies a lot, then I have to look at intermittent things again. So who's to blame? Let's look at the VDI client. The database server showed good performance. The terminal server didn't take so many large breaks compared to the VDI client. Well, a friend of mine, I think his name is Eddie, referred to that as think time, the client think time and the server think time. Well, when I was at Network General, Network Associates, I had the pleasure and the privilege to learn Eddie and Jasper. And we all three hit off for the for the analysis route. I was doing more training, they were doing more consultancy, trying to check performance. Look at them, what happened to them. So the idea was, now let's look at the hardware of the VDI host and the software platform. So the service provider was under severe pressure. So okay, I see a couple of things already in there. In the chat. Now, actually, they tried to improve the VDI host on a test platform, and that really helped. But it still was worse than the baseline. So it helped, but it didn't solve all of our problems, and not all of that. So is there still room for improvement? I think we ended up at a roughly 10 to 12 seconds for this transaction. So how about the database server? And what about that firewall? You already put that into, I shouldn't guess, but the new firewall in the drawing probably points to something. Yes, why not? So we try to do the math. And just, I love drawing pictures. We had 31 seconds for the VDI client. Now we had the task to separate idle client times on the client, add all of those up, and also look at the server side, all the service response time. Now, since that trace was taken on the VDI client, it was on the client side of the firewall. So all requests had to cross the firewall and go to the database server. Now, the round trip time on an average basis was a millisecond, which was quite high for a normal firewall, since it was also a virtual one. So 1 millisecond round trip isn't too bad, but the question is, how often do you need to cross that? Since it's the database transaction, it's the number of turns again. So the client time was 21 seconds. The server time on the VDI was 10 seconds. So that made those 31. Now for the terminal server, where the application actually resided on the terminal server, we had idle times of 6.4 seconds, which made a huge difference. But look at this. The response times from over to the database server and back was, well, the round trip time being 320 microseconds. And to add it up completely, we ended up with a 3.41 seconds. Well, Wireshark looks at the so-called service response time. Well, for the database, there is no service response time calculation. And if I had one single wish to development, it was service response time for every application, for every single port. So we try to do that on our hand as well. Well, it's something I put in the extra files here, but we developed a technique how to calculate that out of a trace file. So we filtered the trace, we export it into Microsoft Excel, and then we pull the data in. And the interesting thing is, on the client idle time, well, we had 21 seconds on the here. The idle time for every single request was just 2.5 milliseconds, but the 10% worth had a value of 20 in total. That means we had those rare events of high idle times. Now, on the server side, we had an average response time of 1.16 milliseconds for Network Plus application. Now, if you compare that to just the ACK times, the ACK is done by the server itself, and the application adds just the minimum extra to it. So basically 9 seconds because of that high round trip time. So this is something I wanted to evaluate a little bit further on. And if you compare that, next slide, and I'm getting to the end, I need another 5 minutes, then I should be done with the resolution of this. Pinpointing one thing that you shouldn't forget in looking at database traffic. Now, this was the terminal server, which was on the subnet of the the terminal server being in the same subnet like the database. So we had the server response time or server think time in total 3.4 seconds. That's an awful. That's really less. Which is we're losing 6.55 seconds across that firewall. Now that rang a bell. Now the effect of the round trip time for one single turn is, well, the difference 1.1 to 320 microseconds. That's not too much. One round trip is worth, well, 777 microseconds. I didn't make up that number. It just dropped out of Excel. Now, if I do that once, it's less than a millisecond. If I do that, well, around 8,560 application turns, it ends up at 6.65 seconds added by the firewall. Goodness gracious. Now, that means the impact of a firewall can get quite high if we end up with a Chatty application. And, well, database traffic, SQL, can become Chatty depending on the, well, on the it's a means of by the art of programming. The programmers on the application decide how many application turns are used or not. 6.6 seconds just by the firewall. Well, this was reported to the customer. Guess what they said? Let's remove the firewall. But in our old data center, we had no firewall at all. So it could eventually help. Is that your solution? Is he right? Is the firewall to blame? Can we remove the firewall? Well, that's a political question within your company. But this is the key. Database applications may have a high number of application turns. So round trip, the number of turns multiplied by the round trip time is the minimum transaction time you end up with. So in our application, the VDI clients had to carry the load of the application. They didn't have enough performance. Well, applications sometimes show a tendency towards terminal services or to VDI. If a terminal services-based application is moved to VDI, massive performance is very often required. It wasn't the only case where VDI systems were too slow. Plus the firewalls added extra delay. Question, and only just because the huge number of turns. So a small increase in the round trip time, RTT, but a huge overall delay. And the question for yourself is, would you remove the firewall, or what else could be done? I rather check whether we could change the application so the application actually showed less turns. Maybe out of those 8,560, maybe trim it down to 300. It was just opening a screen, nothing more. So basically, look at large delta times, high response times, but bear in mind, if there are no high response times that can pinpoint to a problem towards the app server or the database, it could be something else, something different. So round trip time multiplied by the number of turns is my minimum transaction time, and try to keep the delta time to a minimum. If one database server is moved to a different location, the app server has to follow. So basically, database applications, and this is, well, the final slide then. High server response times can point to a slow database. Long client wait time is extra delay on that piece of hardware where the software is, where the application is actually running on. Those database application could be very sensitive to the round trip time. Try to avoid a high number of application turns. Well, one programmer once told me it is by means of how to get to the database. Row by row, every single, record pulled over to the client, every single one, row by row, is slow by slow. Try to improve that if you are doing the programming piece. If you're doing the network piece within an application, try to keep the RTT minimum. And please, well, I'm open to discuss whether a firewall is good between client and server or not. I would have the firewall kept in the place. But this is basically the end of my presentation. Well, 5 minutes, 6 minutes into that. I'm open for the questions. Okay, Graham, can you take over? Have you monitored the chat or
Yes, there was
a question?
no actual questions in the Q&A bit, but a couple of points came up in the chat there, suggestions about what the likely culprit was, trying to guess where you were ending up.
Oh yeah, okay.
I'm just saying that they thought maybe the new firewall might be an issue and so on like that. But,
okay.
Which was an interesting discussion. That the firewall was obviously there for a purpose, but its performance and the chattiness of the application led to the performance effects that you saw overall that customers are complaining about. So then that, as you say, becomes a very much political decision about whether the firewall is achieving anything within the system design.
Yeah, and if the data center is secure enough, and maybe you'd have an TLS or SSL offloading feature in front of the for the incoming connections, you could maybe remove the firewall. But it's a political question. I'd rather say 700 microseconds for a typical firewall is quite high. It was just a blunt packet filter, so there was no IDS running on that. But the performance and the, picking up that a non-software firewall might have helped. Yes, that's something we should have, we could have tried. But if there is enough performance on a virtual firewall, that will also do a job.
So it was just a simple packet filter firewall. It was just restricting IPs and ports, basically.
So, and maybe if I take the last question by Thomas, do you have any tips on how to isolate backend requests, especially when you do some captures for application with multiple users using it at the same time? Very good question. Let me get back to my presentation and to my monolithic approach. And this is key to, well, doing the analysis on database applications. Well, my model was like this. I had a client, I had one app server, I had one database. If there was only one user on the system, I see a request and then the app server would just do a connect to the database, and you would see, well, the first query and the last query and the series of queries on the back end, and then the response coming back. Now, if you've got, and it's a very valid question. If there are multiple users, every user will have, well, a couple of those HTTP requests and responses. And there could be maybe for 100 users, just 3 or 4 or 5 TCP sessions interact, where the app server and the database server would interact. So it is almost impossible to match and map the request from one specific user's transaction to the respective SQL down here. The only thing what I would recommend doing is I take it from a front end. I would start here, identify when the request comes in, check the response, the very first response, not the last one, since the database server and the app server are not responsible for the amount of data to be sent. So when it's HTTP, make sure that TCP reassembly is disabled. And then just between the request and the response, just look at all SQL queries. Look at the number of turns on an average basis. Look at large outages, let's say large think times, just to pinpoint a problem. And also when it's an intermittent problem, that means the performance is quite good at most of the time, but once in a while it gets worse. Then, so there is a problem looking at just one Wireshark trace. I would rather then take the back, just look at the back. Hang on, I need to get back. I would maybe look at the backend traffic overall over a certain period in time and look for some large delta times within that, number of turns, round trip time. Make sure that you don't lose any packets there, and plus, please ensure that app server to database server and back is minimum. And when I say minimum, when the usual round trip time is maybe a microsecond or maybe 10 microseconds, then a couple of milliseconds will be a major increase. If the round trip time was 10 milliseconds, well, just as a baseline, then anything beyond the, let's say 30 or 40 milliseconds will be a pain in the neck. So, but hard to say. And if it's a programmer's issue, then I ask the customer to take one user to a sample, let's say to a test network, and just see whether an application with one user is going well. Then maybe it's a load issue. So, and Marcus, you issued the microseconds or milliseconds. Was that related to the round trip time? I think it came.
I think you might have just misspoke at one point.
Yes. Well, when I learned networking, my request always was, what's the typical time to pass a router? Well, people said a microsecond would be good. It depends on the size of the packet. That's for sure. A microsecond for a router wouldn't be bad if it's a packet filter. On a normal firewall, I'd say maybe not more than 5 microseconds. If there is, well, we got to look at the firewall itself, look at the processes. If there are extra delay in traversing that firewall, could be queuing, could be processing. If the processes are not running smoothly, let's say a firewall usually has got a fast path for a quick transfer and has got maybe a slower path. If the fast path is not utilized, or maybe you got to get your firewall folks into the place. Okay, so I'd rather have a microsecond up to 10 microseconds as a flight time through a firewall, being a normal packet filter
I think we're just about coming to the end of our time today. Thank you very much, Matthias. As you mentioned, you'll be in Discord to answer questions and so on for a while. And any other questions, just bring them up on Discord and we'll do the best to answer them. So thank you very much for your presentation today, Matthias.
You're welcome. So my last slide, sorry, I took, this is case 2, which is at the end of here. So that's a huge thank you for all of you. Please feel free to to enter some feedback. I'm on Discord. Maybe in 5 minutes I will be in the voice channel of Zoom One discussion. If you want to chat with me, continue that, continuing this conversation, I'll be happy to talk to you. So anyways, feel free to Twitter me at Wiresharky or write me an email if you've got any further questions or experience on your end. I'm open to discuss things. Thanks a lot, and thanks for you attending. Bye-bye.
Thank you very much, everybody. Have a great lunch. Bye now.